Hello again. Thanks for joining us on Space Nuts. My name is Andrew Dunkley, your host, and this is a Q&A edition. And questions today coming from Kevin about the emptiness of space. Casey wants to talk about tidally locked planets. Hazel is asking about sonification. We've talked about that in the past. And Rusty. Rusty. Gee, it's good to be back. I really missed you, Rusty. And your questions about bulk motions in the universe. Can't wait.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Joining us once again is his good self, Professor Fred. What's that, astronomer at large? Hello, Fred.
Hello, Andrew. Good to be back, and good to see your smiling face again.
Yes, I've got a smiling face. I'm nearly over the jet lag. You don't smile much when you got jet lag. That stuff's horrible. Yeah. There should be a pill for that. There really should. I don't know why someone hasn't invented one yet. Maybe I should. I'd make billions. I would. Here, take this. No jet lag. Done and dusted. How you been, Fred?
Very well, thanks. I don't have jet lag, and that's good. I guess the nearest to a jet lag pill is melatonin. Some of my colleagues who travel a lot used to insist on melatonin tablets. I've never used them because I always manage to sleep all right. But you're right, jet lag can be a bit fearsome.
Yeah. And you don't want to get the melatonin tablets mixed up with the melanoma tablets because that can be lethal.
That's right. That could be.
That's a terrible joke. See, I'm back. Dreadful jokes. We might as well get straight into it and see if we can solve some of these riddles that people have sent to us. Our first question comes from Kevin. Kevin is a patron and gives me an opportunity to thank all our patrons for pitching in to the show. We really do appreciate that, and we think you are terrific. And if anyone wants to look into that, they can do that via our website, patreon.com/spacenuts, I think is also where you can go. So Kevin's question, how empty is space? Or to ask another way, how is a spacecraft like New Horizons, how is it that it can travel millions of miles through space and risk hitting a grain of matter that I assume would destroy it? And that's a really good question because I've often wondered the same thing. How do we go through space and not get hammered by something and, oblivion?
It is a great question. It's got a very characteristic two-word answer, Andrew, which is...
That's a wonder.
No, or fun. Because, yeah, you're right. How empty is space? It depends. And it depends which bit of space you're in. And so, I think Kevin's right. Thinking about the James Webb Space Telescope, which indeed did travel, it's 1.5 million kilometres, so it's about 1 million miles. That was the distance that it travelled from Earth to its location, because it settled in a region called the second Lagrange point, L2, where there's stable gravitational pull. But one of the other things about the Lagrange points is because they're stable, they attract dust. And so they're relatively dusty regions of space. And actually, within just a few months of the deployment of the JWST, there was a micrometeorite impact. This would be something the size of a grain of dust, maybe even smaller, hitting at maybe 30 kilometers per second that left a permanent dent in one of the mirror segments. Today.
Yes.
They've been quite lucky, actually, because I thought, that was within a couple of months of deployment. I was thinking, my God, if that's the case, we're going to have no mirror at all within a year. But in fact, I think it's been relatively unscathed for the rest of its career. It's doing a fabulous job. We often talk about JWST observations here on Space Nuts. So basically what I'm saying is the Earth's environment in particular is quite dusty, and that's because it's near the inner part of the solar system. There's a lot of comets come from outer edges of the solar system, which shed dust as they get near the sun. The dust is released from its icy matrix, and so comet trails are dusty, and that adds to the general dust that is the remnant of the origins of the solar system. The plane of the Earth's orbit is quite dusty. And so, yes, something like the Webb is going to be always at risk from being hit by a rain of material. But if you go out into the outer part of the solar system, beyond the orbit of Neptune, you get a much clearer view because there's virtually no dust out there. And that's one reason why the New Horizons spacecraft measured the sky background there as being fainter than we have in the inner solar system because there's no dust reflecting sunlight. And that's an interesting experiment. It actually caused a bit of a revision of the number of galaxies that we think the universe has. I'm not going to go in that direction now because it's another can of worms. But what that's saying is that in terms of dust, once you get beyond the inner solar system, then it's fairly dust-free. Of course, there's other stuff floating around in space, lots of subatomic particles. There's the wind of subatomic particles that come from the sun. They can have an effect, not putting a dent in your mirror, but certainly can damage electronics and things of that sort at the atomic level. And once again, that's more true nearer to the sun than further out. So when you get to interstellar space, the average density is pretty low, although interstellar space is populated by giant clouds of gas and dust. And so if you get in one of those, suddenly you've got material around you again. It's still very, very rarefied. It's still better than the highest vacuum we can create artificially on Earth, but it's not empty completely. One of the things, though, that illuminates to me just how empty space is the fact that we can look through space to a time 13.8 billion years ago, when the universe was still glowing brightly. We can still see the flash of the Big Bang, and that's because the photons that were emitted 13.8 billion years ago are still going strong. We see them now as microwaves because the expansion of the universe has stretched them, their wavelength. But that tells you how empty space is. The fact that we can see distant galaxies out to almost the origin of galaxies, and then beyond that we can see the cosmic microwave background radiation. You'd think there will be something in the universe that will make it a bit more opaque than it is, but it is incredibly transparent, which tells you that it's pretty damned empty.
You were also it's been 3 months and I haven't been able to insult Hugh once. So, what you just said also applies to Hugh. Empty, big void, nothing.
Don't know why you're
no reaction. No reaction from you. So diplomatic. Sorry, Hugh. Couldn't help it. Golden opportunity. But in answer to Kevin's question, though, it's pretty sparse. You'd have to be very unlucky to take your $30 gazillion Ferrari spaceship out there and suddenly realise that it's been destroyed by a speck of dust. You'd have to be, really unlucky. Well, hang on. Maybe a Tesla Roadster.
Yeah.
Or something like that. You never know.
That's right.
Thank you, Kevin, and thank you for your ongoing support as a patron of Space Nuts. We appreciate it. Our next question, Fred, comes from Casey, who sent us an audio question.
Hi guys, this is Casey from Colorado again, and today I have a question about tidally locked planets. I know that a tidally locked planet is a planet that always has the same side facing its star, and that this happens because the orbital and rotational periods are the same. What I'm wondering about is how this might affect the formation of compounds and molecules. I hope you're both well, and thank you for taking the time to answer so many of my questions.
Thank you, Casey. It's lovely to hear from the ladies. I know there was a big push on to get more female listeners to send in questions, and that seems to have been very successful. So well done, Heidi. So what is the answer to Casey's query?
I think it's a great question, actually. If you've got a planet that always has one side facing its parent star, that side is going to be pretty hot, but the other side is facing the depths of space. It's facing the cold of space, and it could be pretty cold. You could be way below zero, perhaps 100 to 200 degrees below zero on one side, and perhaps 100 or 200 degrees above zero on the other. Molecules and compounds to form, they like sort of moderate temperatures measured in tens, hundreds, maybe thousands of degrees, not tens of thousands of degrees. So you might find that compounds are not going to form on the sun-facing or the star-facing side of the planet because it's too hot. Compounds just get shredded apart into their component atoms by the energy of the heat. On the other side, it's too cold. So your molecules never kind of get together. There's not enough motion of the gases in an atmosphere for the molecules to come together and react. But in between the two is this region that we always call the terminator. That's the region between the light side of a planet, or the boundary between the light side of a planet and its dark side. And it could well be, because the planet's not rotating, you might find that there the temperatures are sort of, temperate all the time, promoting the formation of molecules and compounds. So for a tidally locked planet, it is possible that you could have this zone around the terminator, which is quite rich in chemical reactions. So, Casey, I think you're onto something there. Maybe there will be this zone that might be habitable, even in what looks like an otherwise uninhabitable world, because one side's too hot and the other side's too cold. You might find there's a zone that's not. So, good question.
Excellent question. Thank you, Casey, and keep them coming. And good to hear from you. And, when it comes to dealing with extreme cold, I'm sure you handle it well in Colorado. I don't know how you do it. Okay. Like we were in Iceland in summer, and I think the maximum temperature was 6 degrees. And I thought, if that's summer, I would hate to be here in winter. That was quite strange. But then I'm not sure if I told you, Fred, but when we were at North Cape in Norway, the northernmost tip of Europe, it was 28 degrees that day. And I looked up the weather records for North Cape, and the highest they'd ever recorded there was 28.4. So we'd nearly hit it the day we were there.
Yeah.
And the locals were freaking out. Like, they thought it was horrible. It's walking around naked. It was so hot. But we just went, oh, isn't this lovely?
So when we were there in January, there was snow everywhere, but it was still unseasonably warm. It was probably more like 6 degrees, the 6 that you had in Iceland. We tend to go to all these countries in the depths of winter so that we get the most darkness and we see the aurora. So you'll definitely have to come with us sometime, Andrew, because we always see it. That's why we're at North Cape. When there was a matter of perhaps 2 or 3 hours of daylight. It was great, though, up there. And you would have stood by that huge Analemma sphere that's right at the tip of the North Cape. We saw that in twilight. But, yes, it was still unseasonably warm. There was snow everywhere, but it was certainly above zero.
Yeah, it's an incredible place. It's one of those like we went around the southern tip of Africa, which is right the Cape of Good Hope, right down south, and then a month later we're standing on the northern tip of Europe. It was quite an incredible trip. Thanks, Casey. Great to hear from you. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Let's take a moment to talk about our sponsor, Insta360, their latest game changer, the Go Ultra. A pocket-sized camera that's redefining how you capture life's adventures. Imagine a camera no bigger than an Oreo, weighing just 53 grams, yet packed with the power to shoot buttery smooth 4K video at 60 frames per second. The Go Ultra's upgraded sensor and AI chip ensure your shots are crisp and vibrant, day or night. Low light scenes? No problem. The Pure Video mode uses AI to reduce noise and boost dynamic range, so your nighttime adventures shine. Battery life? The Go Ultra's got you covered with a next-gen stacked polymer battery. The standalone camera runs for 70 minutes, and when paired with the Action Pod, you get up to 200 minutes of shooting time. Need a quick recharge? Plug it in, and it hits 80% in just 12 minutes. Storage is a breeze with removable microSD cards supporting up to 2 terabytes, so you can shoot to your heart's content without worrying about running out of space. Here's the best part. For the first 30 Space Nuts listeners who purchase the Insta360 Go Ultra at store.insta360.com, you'll score a free sticky tabs accessory to mount your camera on anything from backpacks to winter jackets. Just use the promo code SPACENUTS at checkout. That's store.insta360.com, promo code SPACENUTS. Check the description for links and more details. Don't miss out on this tiny titan of a camera that's ready to capture your world like never before. Now, back to the show.
3, 2, 1.
Space nuts.
And you're listening to a Q&A edition, and our next question comes from Hazel. Hazel says, "Hi, I think we've all heard the musical adaptation of orbits in the solar system, sonification, and how it highlights the beautiful resonance." And she says, "I love this. My question is to do with most orbiting things. Do most orbiting things experience this? Would galaxies orbiting their center of mass also experience this? I feel Kepler, in his genius, got to the bottom of this, but I find it fascinating. Love the show. Much love to you all." Hazel from Scotland. Scotland, what a lovely place that is. Rained all the time. But anyway, while we were there anyway. I remember us actually playing some of that sonification production where they took a photo, a wide-angle photo or image of a portion of the universe, and they applied sounds to the different objects and created this beautiful music. So would that apply elsewhere in other parts of the universe?
So the sonifications that Hazel's talking about are a little bit different from that. And,
Is it something I missed while I was away?
No, you didn't.
Oh, okay.
When I read Hazel's question, I went to that exactly the picture that you're talking about. There's one that I particularly like. It's the galactic center and all the stardust. Yeah, that's linked in West. It's beautiful. And it's pretty easy to find. It's on NASA's website. But what Hazel's talking about is the resonances between the planets, for example, in a solar system, so that you've got a situation where one planet goes round once, the one next to it on the inside goes around twice in the same time. The one on the outside of it goes around a half in the same time. So there's this, what we call orbital resonances. Yeah. And you can sonify, you can sonificate that. And in a sense, it's what Kepler was doing when he wrote Harmonia Mundi, the harmony of the spheres or the harmony of the worlds. He was looking at all these different resonances. And the most obvious in our solar system is with the moons, some of the moons of Jupiter. Ganymede, Europa, and Io are in a 4, 2, and 1 resonance with Io. Ganymede 4 to 1, Europa 2 to 1, Io 1 to 1. So that's basically the sort of thing that Kepler was looking at, because he said, well, this is very similar to the intervals on a musical scale where you've got fourths and fifths, and these make chords that are pleasant to our ears. And so his harmony of the worlds was based on all that. But now we've got so many more examples with these extrasolar planets. And there are some of them that have got really quite spectacular resonances. And I might refer Hazel to a very nice article that appeared on the Conversation a year last February. It's written by a good friend of mine, Chris Impey. He and I were research students together, actually in Edinburgh, the University of Edinburgh. Chris has been Chris has been I'm glad you went there. It's good that you especially had haggis. I think that was very good for you. Yeah. Chris has basically most of his career, as I've worked in Australia, he's worked in the United States, principally at the University of Arizona, where he's a distinguished professor of astronomy. But he's written a lovely article on exactly this. It is called Orbital Resonance, the striking gravitational dance done by planets with aligning orbits. And it's worth looking at because it's got a list of several of the major resonances around planets going around other stars, like Gliese 876, which has got some 4:2:1 orbital ratios, Kepler 233, 4 planets with ratios of 8:6 to 4:3, and there's a number of them. TRAPPIST-1 is the record holder. It's got 7 Earth-like planets with orbit ratios you don't need to know. It's 24 to 15 to 9 to 6 to 4 to 3 to 2. So those are all what we call resonances, and you can turn them into music, and you can have orbital sonification. And so Chris's article has got some nice links to the sonification of these orbits. There's a very nice one that ESO, the European Southern Observatory, has done on one of the systems that they've found. I think it's can't remember which system it is. I think it's TI 178. You'll find a lovely audio of that. If we'd been better organised, Andrew, we might have dug one of these out and played them for the show. But anyway, that's the place to look. It's a great article. It explains it very clearly. Your question about resonances in galactic orbits is very much less easy to answer. We suspect not, because the number of stars in orbit around the galactic center, 300 or 400 billion, means it's more like a cloud of particles that behave in a different way from what individual objects do. It's more like a cloud of stuff going around the center of the galaxy, rather than specific planets with their own center of mass and their own resonances. So I don't think there are resonances to be found in galactic orbits. I'm happy to be proved wrong, though.
Yeah, never say never, Fred. I think it's
never say never. That's right. Yeah.
Yeah. Wonderful. Hazel, thank you. And I must say I loved Scotland while I was there. It was a brief visit, but I'm glad I got to see it and travel from Glasgow across to Edinburgh and back. Lovely part of the world, even though it was cold and wet and wasn't windy. That's the only, it wasn't too windy, but the rest of it was supposed to be summer, Fred. I don't know how people live in the northern hemisphere. Most of the world population lives in the northern hemisphere, and from my experience, the weather's so much worse up there.
If you, yes, that's right. If you drove on the M9, as you probably did if you went by car from Glasgow to Edinburgh, you would have passed the Kelpies. Would you have passed the Kelpies? Yes, you would, I think. They're on that road. 2 huge statues of Celtic water horses. You might have seen.
Yeah. There's also sculptures along there.
That's right. Yeah.
There's a whole bunch of different things. Yes. Yeah, we did spot a few along the way.
Yeah.
It's quite weird ones. They got a great sculpture in Glasgow of 2. Is it shipbuilders? I think they were shipbuilders. Humongous things with giant sledgehammers. Yeah, that was a beautiful statue as well. Thanks, Hazel. Great to hear from you.
3, 2, 1.
Space nuts.
Our final question. Oh, good grief. Here we go. Comes from Rusty.
Hey, Fred and Andrew, and maybe Heidi. It's Rusty in Donnybrook. I'll try and keep it simple, as I always do. The peculiar motion of the local group towards the Virgo cluster and onwards to the great attractor in the Hydra Centaurus supercluster turns out to be the same as the overall supercluster itself, when observed in a co-moving reference frame where the observer is at rest relative to the CMB. Now, the lambda CDM is invoked to explain this enormous peculiar flow. Space was already effectively infinite when matter first appeared 380,000 years after the Big Bang. If we look at explosions in the vacuum of space, for example, a Crab nebula, we find filaments and voids. But in the everywhere all-at-once explosive birth of matter in the highly energetic universe, resulting flows could have happened in any direction. Could this be what we are seeing? See, that's a simple question. Thanks, people. Cheers.
Yeah. Okay. Right. I see. Thank you, Rusty. So good to hear from you. My brain hurts, Fred. I'm very confused.
I was going to let you answer this one, Andrew. I thought you can top this.
I've got an answer for him. Because.
Yeah. There's a few. there's a lot in there that I'm not going to unpick. Thank you, Rusty. Matter actually appeared in the first 3 minutes, not the first 380,000 years. That's when the radiation got cool enough for atoms to form. So it didn't take very long. And you're absolutely right to quote the filaments, because that's what happened. We think that, notwithstanding the peculiar motion of galaxies, which is basically just the gravitational pull of these filaments of dark matter, probably, that's moving them around relative to the expansion of the universe, relative to what we call the Hubble flow. Those filaments seem to have been created very early in the expansion of the universe, maybe during the period of inflation, which is the first gazillionth of a second. Forget 3 minutes. It's 10 to the minus 33, I think, is the number. I think it's the way to look at it. I remember my young nephew some time ago playing with some stuff that was, it's kind of like Play-Doh, I think. And he sort of squashed this stuff, a lump of this stuff down between the table and his hand, and then lifted his hand up. And what you got was spontaneously forming filaments linking one blob to the other. And it's just, it seems to be a facet of something that's expanding. You will get, it probably depends on viscosity, and, well, space-time doesn't have any viscosity. We discussed that in the last Q&A session of Space Nuts, but it's still like it did form filaments, and we can see them today. We see the structure of galaxies on a much wider scale than we're talking about the Virgo cluster, which is really nearby. You see this filamentary, this kind of foam-like structure of the universe, which seems to just have been an artifact of the expansion caused because of slight differences in temperature in the Big Bang plasma. And so the dark matter seems to have formed these filaments. The clouds of hydrogen collapsed onto them. That's where they formed the galaxies, and that's why we're still seeing these galaxies strung out all over the place. So it's not, you don't need you drew the example of the Crab Nebula. You're quite right. There's filaments everywhere with that, and they all seem to radiate out from the source of the explosion. But if you've just got an expansion, you don't need a particular direction for these filaments to form in. They'll just give you this sort of foam of material, which is what space-time is like. And so I don't know that necessarily answers Rusty's question, but I hope it gives him some food for thought.
Yes, or it'll just make him ask another question. That's the problem, isn't it?
No, it's great. It's great that we get these questions.
Oh, just kidding.
Yeah.
Rusty actually sent me some great photos while I was away of, I think, a couple of planets that he observed.
Oh, great.
Night out of WA. So, it was good. So thanks for that, Rusty. But it's always great to hear from you. Your questions are always so far out of left field. That's too much for my brain. But thanks, Rusty. Good to hear from you, as always. And please keep the questions coming in, female and male listeners alike. We love to hear from everybody. So just go to our website and send them in to us. spacenutspodcast.com or spacenuts.io is where you can send text and audio questions. And while you're online, jump around our website and have a look. I don't think anyone's been into the shop for months, so Hugh's just sitting in there surfing the internet and trying to figure out the problems of the world. So, go and sell something, Hugh, for crying out loud. But yes, that's on our website. And we're on Facebook and Instagram as well. If you're into social media, you can follow us there. You don't, no obligation. You don't have to do anything. You don't have to talk to anybody. Just look at the pictures. It's how I studied at school. Just look at the pictures. Yes, that's enough. Yes. spacenutspodcast.com, spacenuts.io, or facebook.com/spacenuts, or the Space Nuts podcast group. There's another group that's very much worth following, because that's where most of our listeners talk to each other if you want to join in. That's enough jibber jabber from me. Thank you, Fred, as always.
Great stuff, Andrew. I look forward to doing it all again next week.
Indeed. Professor Fred Watson, astronomer at large. And thanks to Hugh in the studio, who couldn't be with us today because, he's a bulk motion in the universe and they're pretty slow. And from me, Andrew Dunkley, thanks for your company. Catch you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Missing 3 Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.